today I'm going to talk about bandwidth utilization, which is multiplexing and spectrum spreading. Okay, what is multiplexing? Multiplexing is a set of techniques that allow the simultaneous transmission of multiple signals across a single network. As data and telecommunication use increases, so does the traffic. We can accommodate this increase by continuing to add individual links each time a new channel is needed, or we can install higher bandwidth links and use each to carry multiple signals. So, here is a dividing a link into channels. Okay. In the multiplex system, any line shares the bandwidth of one link. The lines on the left direct the transmission string to a multiplexer MUX, which combine them to a single string many to one. At the receiver end, the string is fed to a real multiplexer MUX, which separates the string back into its copper transmission conjoint and directs them to the corresponding lines. In the figure, the word link refers to the physical part, and the word channel refers to the portion of a link that carries its transmission between a given pair of lines. One link can have many n channels. So, these are the categories of multiplexing. So basically, there are three basic multiplexing techniques, which is the first one is frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. The first two are designed for analog signals, and the last one is for the digital signals. So, I'm going to talk about frequency division multiplexing. We consider FDM to be an analog multiplexing technique. However, this does not mean that FDM cannot be used to combine sources sending digital signals. A digital signal can be converted into an analog signal, which the technique discussed in Chapter 5 before FDM is used to multiplex them. And FDM is an analog multiplexing technique that combines analog signals. So this is the FDM process, the frequency multiplex process. So this illustrates the multiplexer process. Each source generates a signal of a similar frequency range. Inside the multiplexer, these similar signals modulate different carrier frequencies F1, F2, and F3. So the resulting modulated signals are then combined into a single composite signal that is sent out of a media link that has enough bandwidth to accommodate it. Okay, next is the FDM multiplexing example. For the demultiplexing, the demultiplexer uses a series of filters to decompose the multiplex signal into its constituent component signals. So the individual signals are then passed to a demodulator, then separates them from their carrier and passes them to the output lines. So this is a conceptual illustration of the demultiplexing process. Next is the analog hierarchy. So in this analog hierarchy, 12 voice channels are multiplexed onto a higher bandwidth line to create a group. So a group has 48 kHz of bandwidth and support 12 voice channels. At the next level, up to 5 groups can be multiplexed to create a composite signal called a supergroup. A supergroup has a bandwidth of 240 kHz and supports up to 60 voice channels. Supergroups can be made up of either 5 groups or 60 independent voice channels. So at the next level, 10 supergroups are multiplexed to create a master group. A master group must have 2.52 MHz of bandwidth, but the need of cut bandwidth between supergroup increases the necessary bandwidth to 2.52 MHz. Master groups support up to 600 voice channels. So finally, 6 master groups can combine into a jumbo group. A jumbo group must have 15.12 MHz. 6 times 2 for 52 MHz, but it's augmented to 16.908 MHz to allow for cut bands between the master groups. Okay, so next is the wavelength division multiplexing. The WDM is designed to use the high data rate capability of fiber optic cable. So the optical fiber data rate is higher than data rate of metallic transmission cable, but using a fiber optic cable for a single line with the available bandwidth. Multiplexing allows us to combine several lines into one. WDM is conceptually the same as FDM, except that the multiplexing and demultiplexing involve optical signals transmitted through fiber optics. The idea is this: we are combining different signals of different frequencies. The difference is that the frequencies are very high. So this figure gives a conceptual view of a WDM multiplexer and demultiplexer. Very narrow bands of light from different sources are combined to make a wider band of light at the receiver. The signals are separated by the demultiplexer. So, WDM is an analog multiplexing technique to combine optical signals. Although the WDM technology is very complex, the basic idea is very simple. We want to combine multiple light sources into one single light at the multiplexer and the reverse at the multiplexer. The combining and splitting of light with sources are easily handled by a prism. Recall from basic phrases that a prism bends a beam of light based on the angle of incidence and the frequency. Okay, now I'm going to talk about time division multiplexing TDM. TDM is a digital process that allows several connections to share the high bandwidth of a link. Instead of sharing a portion of the bandwidth as in FDM, time is shared. Each connection occupies a portion of time in the link. So, this figure will give a conceptual view of TDM. Note that the same link is used as in FDM. Here, however, the link is shown section by time rather than by frequency. In the figure, portion of signals 1, 2, 3, and 4 occupy the link eventually. Note that in the figure, we are concerned with only multiplexing, not switching. This means that all the data in the message from source 1 always go to one specific destination, be it 1, 2, 3, and 4, or 4. So the delivery is fixed and unvaried, unlike switching. We also need to remember that TDM is, in principle, a digital multiplexing technique. The digital data from different sources are combined into one naturally. However, that does not mean that the sources can produce analog data. Analog data can be sampled, changed to data, and then multiplexed by using TDM. So, TDM is a digital multiplexing technique for combining several low-rate channels into one high-rate one. Next, I'm going to talk about synchronous time division multiplexing. In synchronous TDM, each input connection has an allotment in the output even if it is not sending the data, time slots, and frames. In synchronous TDM, the data flow of each input connection is divided into units where each input occupies one input time slot. A unit can be 1 bit, 1 character, or 1 block of data. Each input unit becomes one output unit and occupies one output time slot. However, the duration of n output time slot is n times shorter than the duration of n input time slot. If n input time slot is t, the output time slot is t, n, where n is the number of connections. In other words, a unit in the output connection has a shorter duration. It travels faster. So the figure shows an example of synchronous TDM where n is equal to 3.
Okay, about multiple slot multiplexing. What is multiple slot multiplexing? This is because sometimes it is more efficient to allocate more than one slot in a frame to a single input line. Why? This is because we might have an input line that has a data rate that is multiple to another input. This is what it means by an input line that has a data rate that are multiple to another. Means that there are multiple input in a data line, input line. And pulse stuffing. Pulse stuffing is making the highest input data rate as the dominant data rate and then add the dummy bits to the input lines with lower rates. For example, these two data input line is 50 kilobyte per second, and then this one is about 46 kilobyte per second, and then to make it equal, we make the highest input data rate, which is 50 kilobit per second, as a dominant, and then for the 46 kilobit per second we add another 4 pulse stuffing. This is called pulse stuffing to make it 50 into 50 kilobit per second. With this we can make the output into 150, so it is equal. Spread spectrum. Spread spectrum is combining signals from different sources to fit into a larger bandwidth. Okay. It is also designed to be used in wireless applications such as LANs and WANs. And in this type of applications, we have some concerns that outweigh bandwidth efficiency. In wireless application, this is the example of spread spectrum. In the wireless applications, all the stations use air or vacuum as the medium for the communication, and then the stations must be able to share this medium without interception by an eavesdropper, and without being subject by jamming from a malicious intruders. For example, in military operations. Okay, now we are moving to frequency hopping spread spectrum, FHSS. Frequency hopping spread spectrum is a technique which uses m different carrier frequencies that are modulated by the source signal. At one moment, the signal modulates one carrier frequency, and at the next moment, the signal modulates at another carrier frequency. Although the modulation is done using one carrier frequency at a time, m frequencies are used to build a long run. And then the bandwidth occupied by a source of the spreading BFHSS to B. Okay. In this example, a pseudo-random code generator, which is called as pseudo-random noise, which is PN, creates a k-bit pattern for every hopping period, and the frequency table uses the pattern to find frequency which will be used for this hopping period, and it passes it to the frequency synthesizer. Oh, it's a bit tongue twister. And now the frequency synthesizer creates a carrier signal of a frequency, and the source signal modulates the carrier signal. Suppose that we have decided to have 8 hopping frequencies. This is extremely low for real application, because in the real implementation there are a lot of signals in network, and it's just this is just for illustration. Okay, this is what it meant by hopping from one position to another. This This is called hopping. Okay. This is what we meant by if the hopping period is short and a sender and receiver can have privacy. This is because when the intruder reads this data, and then when the frequency hop to another position which is at the 900 kilohertz, the data will be different. Okay, and after that the hopping comes down to 300 and then 200, and this makes the data becomes a bit mixed up, because at the 700 kilohertz frequency the data is different, and then when the intruders read the data at 900, it will be different, and then it's the same at 300, 200, 400, because the data at every sequence, every frequency is different to each other. Means that the intruders will get headache when it comes to this, because he or she read different data and cannot be passed, cannot connect each other. And the final subtopic is DSSS, which is direct sequence spread spectrum. Direct sequence spread spectrum is it expands the bandwidth of the original signal, but the process is different. In DSSS, we replace each data bit with n bits using the spreading code. In other words, each bit is assigned a code of n bits called chips, where the chip rate is n times of data bit. In this example, it shows the concept of DSSS. This is a technique which expands the bandwidth of the original signal, but the process is a little bit different. In DSS, we replace each data bit with n bits using a spreading code. In other words, each bit is assigned code of n bits, which called as chips, where the chip rate is of the data is n times of the data bit. As example, we consider the sequence used in a famous Barker sequence, which is wireless LAN, where n is 11, and we assume that the original signal of and the chips in the chip generator use molar and RZ encoding, and then the chips and result of multiplying the original data by the chips to get the spread signal. This is the example of DSSS. Multiplies from original signal with the spreading code to get spread signal. We use exclusive OR to get the spread signal. How to do it? This is considered as 1 times 1 becomes 1. 1 times 0 becomes 0. 1 times 1 becomes 1. So it means by multiplying original signal to get with the spreading code to get the spread signal. Remember to use exclusive OR to get the spread signal, EOR, or this symbol. It's the same with 0. I only take until this. 0 times 1 becomes 0. 0 times 1 becomes 0. 0 times 0 becomes 1. 0 times 1 becomes 0. Okay, this is how we get the spread signal. Okay, and finally from me and Haiza for the summary of our presentation is Bandwidth utilization is the use of available bandwidth to achieve specific goals, and the efficiency can be achieved by using multiplexing. Privacy and anti-jamming can be achieved by using spreading. And multiplexing is the set of techniques that allows the simultaneous transmission of multiple signals across a single data link. And in a multiplexed system, lines share the bandwidth of one node. And that's all from us. Thank you for lending us your ears and eyes and mind to focus on.